Hey everyone, thank you for waking up so early after last night's boisterous party. Welcome to the first talk of the day. I am Bill, talking with my colleague Daniel about a pretty interesting iOS in the wild persistence exploit that we found, and we'll tell you all about it. So first off, my colleague Daniel and I are from an organization called Citizen Lab. This is a picture of our building at the University of Toronto. At the Citizen Lab, our mandate is to study novel technological threats to human rights. So this includes things like internet censorship, chat app censorship, as well as the sort of stuff that Daniel and I work on, which is targeted threats. Spyware, hacking, phishing, sophisticated attacks employed against dissidents, human rights activists, journalists, etc. So one company you might have heard of, NSO Group, is part of a burgeoning mercenary spyware industry, which sells sophisticated hacking products to governments. And the sales pitch is, hey, governments, you want to monitor criminals and terrorists, and they're going dark. They're using Signal, all these pesky encrypted apps. You can't find out what they're talking about unless you hack their device. So they sell a product called Pegasus. And Pegasus is essentially spyware that allows the government operator to see everything on the phone and even create new information, like turning on the microphone to record meetings, turning on the camera to take snapshots of your face, I guess. So the reality is a little bit different than the marketing, right? In addition to perhaps being used against criminals and terrorists, Citizen Lab, as well as our peers in the public interest cybersecurity space, have documented widespread abuse of the spyware, not only to target criminals and terrorists, but also dissidents, human rights activists, lawyers, not just one government suspected of abusing this, but governments all the way from the Americas, Africa, Europe, Middle East, Asia, you name it. Not only is the stuff abused to spy on dissidents and journalists, though, sometimes it's used in a much more personal vein, sort of like stalkerware. There was an interesting UK court ruling a couple years ago, which found the Emir of Dubai responsible for hacking the phones of his ex-wife and her lawyer, who's a baroness in the UK House of Lords, during a child custody proceeding, found to have hacked their phones with NSO's Pegasus spyware. And of course, other interesting cases of people who are not criminals and terrorists, I suppose, depending on your view on international relations. French President Emmanuel Macron, UK Prime Minister Boris Johnson, said to have been targets as well of Pegasus, showing that this is used also for more traditional foreign espionage. So how do we track all this stuff? Well, way back in 2016, when we documented the first case of Pegasus in the wild, it was a little bit easier. So a human rights activist by the name of Ahmed Mansour in the UAE received a dodgy-looking text. And he was like, this is odd. I'm getting a random text with a weird link from a number I don't recognize about human rights issues in the UAE. This looks strange. So he forwarded it to us. We clicked on the link in a controlled environment and got a chain of 3 zero-day exploits plus the Pegasus spyware implant. Nowadays, it's a little bit trickier. There's been a shift away from these sorts of one-click exploits more towards zero clicks, which means remote, interactionless. Target doesn't have to do anything. They don't notice anything, as illustrated here by this funny XKCD comic from 2021 about a zero-click exploit that NSO Group deployed against iPhones. So back in 2016, it was a little bit easier, right? We could work with potentially targeted organizations and say, hey, if you get a dodgy text or email or something, call us. Now it's a little bit trickier. We have to do sort of more proactive outreach and phone checking, doing a check of log data on the phone to see if there's evidence of compromise. But fortunately, we have a little bit of help in the form of these threat notifications that Apple and other entities send out saying, hey, we think your phone's being targeted by spyware. You should get stuff checked out. So how does this zero-click stuff work? Well, I will give you a very brief and hopefully correct history of zero-click on iOS, but please do submit any corrections to me after the talk. I'm very curious. So the first publicly reported zero-click attack on iOS was in 2016, and there's no technical details about this, but a Reuters report about the UAE's hacking operations mentioned that the UAE government purchased a iOS zero-click from a US-based company and was going wild hacking people around the world with this. The way that these sort of early zero-click exploits are believed to have functioned is via parsing bugs in the way that iMessages are encoded. So iMessages are represented as these extremely complex, very juicy attack surface object of NS-keyed archive. And there were tons of bugs. Google Project Zero found a ton of these in 2019 when they set out to sort of do a clean room implementation of, if we were to build an iOS zero-click exploit, what would that look like? So they found a ton of attack surface on NS-keyed archive, got, I don't know, like between 5 and a dozen CVEs fixed, and set off a sort of paradigm shift as Apple introduced tighter sandboxing around parsing of iMessages. After that, we saw threat actors go with sort of other bits of the iMessage chain, for instance, attachments to the messages, not the actual message itself. So issues with image parsing of PDFs, WebP, font parsing with Operation Triangulation, as well as the suspected audio parsing bug that Apple patched recently in iOS 18.4.1. And a couple other ones which we were able to sort of document through log analysis, but we weren't sure of the specific core cause of the vulnerability. For example, issues with around CalDAV or XML parsing for iCalendar, issues in the Find My and HomeKit app, which interestingly, the HomeKit app also had some NS-keyed archive dimension there. But anyway, once you've hacked the phone and the target doesn't notice, how do you keep your spyware running in the event that the phone gets rebooted or updated, et cetera, et cetera? Well, it turns out that it's really hard on iPhones to do sort of capital P traditional persistence, just like launch a binary when the phone runs, right? You can read all about this in Apple's platform security guide. It's very verbose. They have tons and tons of, cryptography and fancy stuff that makes this hard. So instead, threat actors tend to focus on just re-exploiting the device on reboot. So Pegasus had a pretty clever way of doing this to run JavaScript on boot. Ran a JavaScript exploit, which was essentially the same JavaScript exploit delivered in the initial vector. Predator did something similar in 2021 with iOS shortcut automations to automatically open a WebKit in the background when the phone starts. Or if you have a zero-click, you as an attacker can just remotely detect, hey, the phone's been rebooted, fire the zero-click again, like we saw with Kaspersky's report on Operation Triangulation. So one of the things, though, even though the spyware is persistent in some cases, it's also very hard to detect because it sort of self-destructs or can be remotely uninstalled. The way that a lot of the spyware is licensed is, you have like 10 concurrent infections or 20 concurrent infections. So when you want to spy on target number 21, you have to uninstall and delete the spyware from one of the existing targets. So it was kind of a mystery to us in 2024, last year, when we just kind of randomly decided, hey, let's put some signatures, ZR signatures for Pegasus on VirusTotal, and we got a match. And this was very strange because how could this sample have been uploaded to VirusTotal? This is not like like a link or an email attachment where it's the way that it got on VT is very clear. These more sophisticated mobile samples, typically, the attacker will have some, dedicated infrastructure, an infection server, which has a template or a template of a sample or the sample itself, compiles the sample, sends it through an end-to-end encrypted channel to a victim device where it's installed. Maybe it persists, but at some point it's removed, and then it's nowhere. So how is the sample gotten? Well, what we think happened is maybe the removal didn't actually happen, or like the code for the removal didn't exist or wasn't invoked properly. So then later, someone connected a forensic tool, perhaps from our friends at Celebrate, made a full file system extraction, and the person who got this full file system extraction decided to upload it to VirusTotal for some reason. Anyway, the sample, interestingly, was uploaded alongside a database, which confirmed the fact that it was a Pegasus sample because it mentioned websites that we had tracked as part of NSO Group's infection infrastructure. The other interesting thing is it was old. So this sample was iOS 10.3.1, iPhone 7. We're talking 7 years old, 2017, in 2024. So with that, I'm going to pass it over to my brilliant colleague, Daniel, who dug in to the nitty-gritty of the sample, and what he found is, and how he found it, is quite interesting.
Thank you, Bill. So the starting point of the technical analysis were these two files, Babylon and Genesis, one an ad hoc signed iOS Marco, and the other a compressed property list, a plist file. Of course, we reverse engineered the Babylon binary, for the most part pretty straightforward. It can run in different modes. The main ones are Babylon mode, which sabotages diagnostics, patches AMFI in order to disable security, and then spawns a binary from disk, either Golden Gate or Tower. And Persian mode, which sabotages diagnostics as well, and then loads the Genesis data file to build an exploit from it. And it will insert that exploit into a file called user.plist. User.plist is a file location D uses for persisting stuff related to calibration. And Babylon stores the exploit blob under the stride calibration data bins key. Babylon also marks the user plist with a modified untether entry, which is a clue that we're most likely looking at what the jailbreaking community calls an untether, a persistence mechanism. So that exploit blob is generated from Genesis, the other file we found on VT. Genesis contains some numbers, fix-up values, a range, an RPS ticked, plus a template for the exploit blob. However, the code that builds the exploit from it did not make much sense. Weird calculations, weird data structures, weird tuning of a constant. Sure, it looked like it's building and rebasing many small copies of a small ROP chain, probably to break ASLR, but a lot of things did not really make sense. So we lifted this code into Objective-C and reconstructed the exploit blob without fully understanding how this works. So we now had the exploit blob. It's an NS-keyed archiver archive, which contains serialized objects. And keyed archiver, as Bill mentioned, of course, is notorious for its vast attack surface. So a reasonable guess is that this exploits some deserialization vulnerability in location D. These archives are super annoying to make sense of manually, but we can decode them with appropriate tooling. So this is the high-level object structure. This deserializes to. We can see top-level array, date formatter, bundle ODR tag, set, arrays, another formatter, and a hash table containing like 300 string proxies. This all looks a little bit suspect. It's certainly not what we'd expect location D to store in that blob normally. And the last 4 string proxies in particular are interesting. 2 of them contain buffers generated by the code we lifted, and 2 of them contain larger ROP chains, around 200 kilobytes large. So cool, but we still don't even immediately know what the vulnerability is here. But even without understanding the exploit, we can reverse engineer the ROP chains. This is the shortest chain, the one that's being constructed and copied around by the code in Babylon. Of course, it's more useful to look at this as integers. Many of these look like pointers, specifically pointers into the dynamic linker shared cache, which is this huge file mapped into every address space containing all of the system dilibs on iOS. And knowing the iOS version and the hardware model, we can pull the matching system image and resolve the pointers. And sure enough, this looks like a ROP chain, or rather a job chain for jump-oriented programming, as most of the gadgets end in a branch to register and not a return instruction. The pointer at offset 0 points to a string, which might be an Objective-C selector, a method name, locale. The rest does look like gadgets or padding, so this checks out. We run into a problem here. We don't know the initial register state, and we don't know where these gadgets branch to. We can make guesses, like X12 probably holds the address to this job chain, which would then give us this execution flow, not quite linear. It's, of course, way too time-consuming to reverse these chains manually, especially the larger ones. So we had 3 job chains with disassembled gadgets, but still no idea what they were actually doing. And even if we'd spent the time to reverse them manually, we'd still be in the dark about the vulnerability and how ASLR is broken. So to run this exploit, we tried getting hold of an iPhone 7 running a particular version of iOS 10. But apparently in 2024, that's kind of difficult. So we were not successful, unfortunately. We decided not to get help from Apple, nor from Corellium, or Cellbrite now, I guess, with the recent acquisition. So without the ability to run the exploit, can we maybe make use of Binary Ninja for static analysis of the job chains? Relocating the gadgets to contiguous memory breaks the machine code and seems hard. But what if we treated each gadget as an instruction in a virtual instruction set composed of all the gadgets? We could use the existing ARM64 plugin to disassemble and lift to LLIL, and Binary Ninja, hopefully, would do the rest of the magic for us. One challenge here is that you don't know what the next instruction is going to be for most of the gadgets. They all end in a branch register, so you end up with a lot of tiny basic blocks and unknown jump targets, unless you track known register state, partially emulating the machine code. So we tried that, and it kind of works. We have a fancy viewer for disassembled gadgets now. But the more interesting lifting stages in a decompiler won't really work well for job chains, so not in this way anyway. For many reasons, some of the challenges are probably solvable by smarter people than me. But this very quickly started to look more like a PhD than a weekend project, so we shifted our focus to emulation. So this time, more serious emulation using Unicorn. We do need to figure out how to load the dynamic linker shared cache into memory and perform fix-ups. But other than that, this should be not too hard, right? Just load the chains into memory and jump to the first gadget. Of course, there are challenges here too. Again, we don't know the initial state of registers, the stack, and the heap. And these job chains do make a lot of calls into Apple code. A lot of stuff there is broken without having been initialized properly. Things like memory allocation, the Objective-C runtime, higher level frameworks. And the fundamental problem remains we won't be observing the exploitation this way. So more thorough emulation was needed. This time, instead of the job chains and the shared cache, we map location D and the dynamic linker, set up some stuff that the linker expects, and let the linker handle the rest, like loading the shared cache and performing library initialization. That should give us an environment where we can emulate the exploitation. Turns out to execute the binary and its dependencies on an emulated CPU, we do need a fair bit of kernel and other infrastructure, something like 130 system routines. In this case, for instance, VFS, virtual memory, including ASLR, mock IPC, relatively complete, while stuff like system control or the various kernel mix-up systems only very minimally. But I do think it's super cool having working libdispatch, the ability to emulate highly asynchronous code, running on dispatch queues, or having MIG and XPC fully work, giving us the ability to simulate higher layer system services. So with this emulation capability, we can watch the exploit in action. And this is the very point in time when the first drop chain, or job chain, I should say, starts executing. We can see the executed instructions for the first few gadgets in the chain. We can then go back to the function call that ended up executing the job chain and look at the call stack, and that's already super helpful in understanding what's going on. We can see that the exploitation happens fully within Foundation's deserialization code, not in location D code afterwards, which is good news. And we can see that the involved classes are set, array, person name components formatter. These should look familiar. we can go back to the keyed archive or object hierarchy to see what's happening. Here's the set. The set is deserializing its constituent arrays and then checks them for equality, which in turn causes the arrays to check if their contents are equal, which eventually calls into is equal to formatter of the person name components formatter with the hash table as the other argument here. And because this code does not check the type of the argument, it then performs an unsafe direct access of the private field of the argument, which results in whatever value that hash table stores at that offset to be misinterpreted as an object pointer. As a result, this code here gets passed a dangling pointer as an argument and calls the locale selector on it. So when the Objective-C runtime is resolving that call to the locale selector, it performs a lookup in the method cache of the class of the object. But instead of accessing the method cache for the private object in green here, it's actually walking other stuff in memory that just happens to have the same shape in red. The runtime ends up using data under the exploit's control as a fake cache. And the fake cache is actually split across two memory regions, a smaller one consisting of 4 pages and a much larger one. The object hierarchy in the keyed archive is such that these two allocations happen to end up in adjacent memory with the magazine allocator of iOS 10. So the lookup in the fake cache is also how the exploit breaks ASLR. The fake cache contains an entry for every possible slide value. Each entry consists of the selector with that slide applied, plus a small job chain rebased to that slide. When performing the selector lookup as part of resolving the method call, the Objective-C runtime will calculate the starting index from the selector pointer. It will then perform a linear search in the cache until it finds the cache entry and starts executing the job chain instead of the method implementation it expected to find. I've skipped some detail here. This technique has been covered in 2016 in a FRAC article by Neil Archibald. The fake cache is 16 megabytes and contains close to 18,000 entries. So does this perfectly break ASLR for all possible slides? Actually, yes. That matches the ASLR range for this particular device in the OS. The range is the wiggle room of the shared cache within what's called the shared region. The slide for the entire shared cache is randomly chosen after boot. And it's the same slide for all processes. For this particular device in the OS, there are exactly 17,925 possible slides. Except there's a small discrepancy here. The exploit has 17,924 entries in the fake cache. So there's actually an off by 1 error here. If the missing slide is chosen, then bad luck location D will crash loop. So assuming the heap grooming works every time, this exploit has a reliability of 4 nines, which would be super easy to fix. So NSO group, if you're watching this, I have a trade offer for you. You give me Git access, I give you a bug fix. So anyway, we use the emulation capability to emulate everything. I'll walk you through the big picture real quick. Location D loads its user plist, gets exploited, executes job chains 0 and 1. Chain 1 will then XPC over to sysdiagnose in order to exploit it with the very same vulnerability. Turns out sysdiagnose back then had an XPC endpoint that deserializes a keyed archive from an XPC request. Chain 2 will then spawn Babylon, and Babylon will finally spawn the Pegasus implant loader. The detour via sysdiagnose is needed because of its entitlements that allow patching of AMFID to accept ad hoc signed Marcos, which we need to run Babylon. And Babylon, also with privileged entitlements, will patch AMFID more thoroughly to allow Pegasus to inject into other processes later on. So before I hand back over to Bill, let's quickly look at when and how Apple fixed this. The bug was introduced in iOS 9, and Apple silently patched it in iOS 10.3.3. So no bug bounty for us, just exploit archaeology. Of course, in addition to this direct fix, later improvements to iOS security in general would have broken many aspects of the persistence mechanism as implemented. Things like core trust or pointer authentication in iOS 12, and many other improvements.
Thank you, Daniel, for that fascinating explanation. So one of the other interesting bits that we learned from looking at this sample beyond the exploit and how it worked was perhaps something about exploit sharing or the exploit ecosystem. So we noted, Daniel referred earlier to sabotaging diagnostics. So there was a single function in this 2017 Pegasus code that did two things. The first thing it did was it added entries to a particular plist to prevent the OS from recording telemetry about certain types of crashes by setting the count limit for those crash types to 0. Additionally, the same function did one more thing, which was a little bit odd. It set a managed configuration value for allowed dictation to false. Apple's documentation says, if false, the system disallows dictation input. This is the annoying microphone icon that you might tap on your keyboard and it pops up, do you want to enable dictation? And you have to say no, and it's kind of a pain. But this struck us as odd. What is this doing in a function that is disabling diagnostics? Well, fortunately, we just happen to have a part of a Pegasus sample from 2018, no exploit, but mostly the same function for sabotaging diagnostics, except instead of setting allowed dictation to false, it sets allowed diagnostic submission to false. And of course, as you can read in Apple's documentation, this has the expected effect of not sending diagnostic reports to Apple, so Apple doesn't get crash telemetry on juicy, things that are going on the device while it's infected with spyware. So what happened here? Why does the 2017 sample have allowed dictation? Why does the 2018 sample have allowed diagnostic submission? Well, there's three natural hypotheses. The first is, well, maybe iOS had a bug as of 10.3.1 where it didn't submit diagnostics. It misread the value for allowed dictation instead of allowed diagnostic submission. So we checked the code. We couldn't find that bug. The second hypothesis as well, allowed dictation might be something else that the exploit needed to do unrelated to sabotaging crash reporting. But the fact that it was updated later to change dictation to diagnostic submission sort of tells against this and suggests a third hypothesis, which is that there was just a typo in this early version of the code. Okay, a typo. We've seen, the off by one error. Devs make mistakes. But what gets a little bit more interesting is some of this code appeared to have been shared with other threat actors, non-NSO threat actors. So back in 2017, at least, there were a couple of regional iOS threat actors. These are our names, Shadowbird and Sunbird. There's no public technical reports on these groups or their implants yet. But Shadowbird was sort of active in generally the Middle East. Sunbird was sort of active in Southeast Asia doing iOS campaigns. And it turns out that Sunbird, we have a sample. They had the exact same function, not just doing the same things, but the exact same code for disabling diagnostics as the 2017 Pegasus with that same typo of setting allowed dictation to false. Furthermore, Sunbird, again, not related to Pegasus or NSO group, had this, what we didn't see an exploit in the sample itself, but there were strings that were shared with the user.plist exploit that Daniel just talked about, specifically a string user_aside.plist, which was an intermediate file name used by the exploit. That's not a common name. This is just some random implementation choice that the exploit developer made. So the fact that we see that shared to us indicates that it was not just the same exploit, but the same exploit code for persistence shared between Pegasus and this Sunbird threat actor. Furthermore, the Shadowbird threat actor, the Middle East one, we don't have a sample, but we found that targets had allowed dictation set to false, and they were negative for Pegasus and Sunbird. And there was no evidence on those phones of user.plist stuff going on. But at least that indicates to us that there was perhaps some entity that was supplying all three of these threat actors with similar, or in fact the same, code for exploits and post-exploit stuff. Now, was this an exploit broker? Was this a shared trust community or something else? It's a little bit unclear. We just sort of can see what was likely shared and not shared. So what we think was shared was the crash reporter or the diagnostic sabotage source code and the persistence exploit source code, at least with Sunbird. What was likely not shared was the actual implant code or the surrounding code for the exploits. So this suggests a couple of interesting takeaways that I'll leave you with. The first thing that I think we learned is that these sorts of parser deserialization vulnerabilities are useful, of course, for initial access. We know that. But they're also useful for persistence, too, by re-exploiting the device on reboot. Yes, but we don't really see a whole lot of persistence on iOS. Perhaps the fact that these exploits are dual use, both for initial access and persistence, maybe using them for persistence is too risky in terms of capturing and burning the exploit, or persistence just isn't required. You can persist perhaps via cloud access, via stolen tokens from the phone once you infect the phone, steal the tokens, maintain cloud access, or you can just reinfect if you have a zero-click. Furthermore, exploits might be more widely shared than reported, and people who are doing attribution should carefully explore the boundary between exploit and exploit adjacent and other artifacts. For instance, user.aside.plist, great exploit fingerprint, because this is not a common string, but doesn't uniquely identify the threat actor. It could be Sunbird, could be Pegasus. Whereas things like Golden Gate or Babylon, the implementation choices of the implant might be more likely to uniquely identify the actor. Well, I think we're unfortunately out of time, so we'll leave you with that and welcome any questions during the coffee breaks or offline. Thank you.